We'll start the session, so please be seated. Um, Okay. Good morning, everyone. Thanks for coming to Korea AI Summit 2023. Um, uh, it is being broadcast online at the same time. So those who are watching online, you can select the cluster you want and watch the sessions. Uh, this is a cluster 3 session, and the title is AI for Scientific and Social Challenges. And our first speaker is Dr. Mark Peters from IBM. He will be talking about AI costs energy and does energy need AI, a very intriguing title. Um, Mark Peters is a distinguished engineer at IBM, over more than 29 years of experience focusing in energy, environment, and telecommunications. So please welcome Mark Peters with warm hands.
Hello and good morning, everyone. Thank you for having me, and thank you very much for the invitation for this AI Summit. So I'm back in Korea. It's second time for me to be here. Last time was 4 years ago. I think it's just good to be back here. My name is Mark Peters. I'm an IBM Distinguished Engineer. I'm working for some time already with IBM. And for all of you that don't know IBM, so IBM is an AI and hybrid cloud company. And we are having a very long-standing commitment already for the environment as well. And that's why I also selected that topic for my talk today, as it is aligning technology, sustainability, and trustworthiness. So with the long-standing commitment to energy, we see that IBM has been very engaged since more than 50 years in sharing and shaping messages and technology for the environment. And we have also set our environmental goals and are working towards achieving them. In addition to the environmental goals, we are also looking at our societal responsibility and have clearly said that we will train more than 30 million people worldwide in technology. And most recently, we also said that we will train 2 million AI experts as we see a need for more expertise and growing expertise in the future. AI costs energy, and does energy need AI? That's the topic of my talk today. And before I go into that one, I just wanted to raise a message here in a different perspective than just energy. So energy is often, at least in the country where I live or in the region where I live in Europe, something that is directly associated with CO2 emissions or greenhouse gas emissions. But interestingly, looking at what's happening in the last 1 year, we saw an increased use of water in data centers. And that was going between 20 and 30% more consumption of water than it was beforehand. So it looks like the use or the massive use of AI has had an impact on how we work with water. And looking at this small bottle, I think it's half a liter of water. This is comparable to what is consumed in water when you are using nowadays some large language models and some prompts for 5 to 15 prompts that you are setting. So assuming here also in the audience, everyone has used ChatGPT or the like tools that we are having nowadays. So each time when you're just prompting them, think about not only the values that you get back, but also the impact that you have on the environment, on energy and CO2 emissions, but specifically also on water. Because I think personally water is something that is more than necessary for us to live. And it's often not so much of the high value message that we see within the industry, but also within society. So 4 years ago, I was here for an event that was not in Seoul, but in Gwangju, so more in the southern part of Korea. It was called Big Expo. It was held by Capco. I was an invited speaker there as well. And I thought it would be good to give you an introduction for my speak today based on what I have shared 4 years ago, because I think predominantly core messages are still the same, whereby there are some significant differences as well. So the core message is mainly that data is crucial to have a high quality AI output. And that was true 4 years ago. It's still true nowadays. I think it's perhaps even more true nowadays than it was 4 years ago. Then for the energy industry, and specifically the electricity industry, there were numerous use cases to apply AI to processes and to the business. But you already hear that it was about AI applying to something. So adding AI capabilities to existing processes, existing technologies, and existing work, whereby nowadays we think more about a complete change in that perspective. So instead of adding AI to something, we think about AI first and having AI as a foundation for a transformation of the industry, transformation of how we work, and transformation also on how we can work with data overall. So the main messages that you see on the right-hand side are still relevant, but keep changing your thinking on AI plus compared to plus AI. So plus AI means you are adding AI to something that is already existing, whereby AI plus puts AI in your first context and adding specific use of that material afterwards. So one of my last statements 4 years ago was that data is oxygen. At that time, often we were talking about data as the next natural resource, or data as a next fuel, or data as the next oil. I thought thinking about energy and thinking about sustainability, talking about oil would not be the most or the best fit in terms of the summary. That's why I thought data is oxygen is much more appropriate, because it provides the oxygen for energy companies to breathe and to live and to work. But it also provides the oxygen through the energy transformation into our societies and into the environment. And that's why I thought the term of data is oxygen is absolutely relevant 4 years ago, and it is even more important nowadays. What you see on the right-hand lower side, it's about the data architecture from the business perspective. I think that one is changing based on the AI plus pattern that I mentioned beforehand already. But let's go into a bit more depth into what I mean here. So looking at today's use of AI in the energy industry, there are a couple of straightforward use cases that come to our mind based typically on the capabilities that we see are available through large language models. So all of these use cases are in fact linked to natural language processing capabilities and are injecting a lot of enterprise data together with existing LLMs. So this, if you put it at an abstract level, is quite similar to what you'll see also in other industries. But I'm personally convinced these are only the first initial trials to apply this new type of technology and paradigm to an industry that is already older than 100 years. And we see that looking at the different foundation models that we can imagine, we have only tipped the first part of the iceberg here. So we are only talking about the natural language and dialogue aspects. These are kind of low-hanging fruits to work with and have first interactions with the technology. But ultimately, we can broaden that spectrum into the two directions that you see also here on the circle. So on one side, it's going on to the images and the speech side. So images has already been something that has been used for quite some time in the energy industry for analysis of the assets, for example, and also for understanding what the real situation of the assets is all about. But looking now at the possibilities with foundation models and images, there are numerous more possibilities to be applied in that context. Then we also know, and I mentioned that the industry is rather old, there is also a need to work with application modernization application modernization technologies, and that's where programming languages are coming in, or AI-assisted coding aspects. So supporting the teams in understanding what someone has written as part of a code 10, 15, 20, or 30 years ago, and then put it into the new context. It will also help to overcome some of the demographic challenges that we see within the countries and the industries, where those who have built up the systems 30 or 40 years ago are now going for retirement very soon, and that skill set is no longer available. Then from a business perspective, I think that geospatial aspects are very relevant for the utility industry. You can think about vegetation management as one of the use cases, but it's also about understanding where to put wind turbines, for example, specifically in more crowded areas, and how the impact is onto the environment. Then obviously, if you broaden the spectrum of energy companies more going beyond just the electricity providers, it's looking at new materials that can be used to build up batteries, for example, but also to build up the renewable energy assets that are required in the future. So just want to highlight this aspect of different type of foundation models. So if we go beyond the LLMs, I think there is a chance for us to look at additional use cases. And IBM has been working here together with NASA and has created a first foundation model that's also available through Hugging Face, and that provides a possibility to be applied in multiple use cases that are going beyond the natural language processing interaction. And it's also not only targeting specifically energy companies, but there's a field of application that can go into insurance companies. It can be relevant for municipalities and communities and governments. It can be relevant for the agricultural sector. So a lot of possibilities that is arising from this new type of technology, not just specifically for an energy company. And that's also the reason why I picked up another old image from my archive, where we see that the energy industry has been changing. So it's going from a hierarchical approach from generation to transmission, distribution to consumption into something that is much more distributed. And we also have seen that there is a network of information and network of technology in that energy system that has been applied. And on the right-hand side, a lot of this information is giving you the impression and view that it's not only about the energy, but it's about the cross-industry fertilization of possibilities. So that was absolutely true already a few years ago when we looked at the business to consumer space, or the home environment, where a lot of the industries are coming together. So it's a telecommunications industry, it's the energy industry, media and entertainment, it's home automation, it's security, it's healthcare, elderly care, insurance. So a lot of industries that are available, that came to your home, and there was a convergence of this industry happening. I think we see this happen now again, because if we think about transformation of the energy industry in nowadays, this cannot be happened separately. So electric vehicles, for example, you see this here in the middle of the chart, is something that is kind of a cornerstone in terms of how the transition can happen. You need electricity, you need to have charging possibilities, you need to figure out, is there a car to the grid possibility or vehicle to grid possibility? So have additional assets playing an active role in the energy system and not just a passive role. And we see this not just with vehicles, we see this also with charging stations that are now more and more equipped with battery technologies. We see it with solar parks that will also have battery technologies. So there is a new type of exchange and interaction between the different industries that is arising and that is really happening. And we see also there a huge potential for AI in that space, because the more player you have, the more data you will have, the more there is a need to automate some of these activities, and automation will take place through the application of AI technologies. Now, when we talk about the transformation and the transition and new technologies, I think one of the major aspects is to raise the awareness of that change and that possibility for all of us to play an active role. And I am leading an IBM initiative that we call Responsible Computing. That's something I've been leading now for almost 3 years. It's a global initiative where we have been collaborating not just with an IBM, but also with a whole bunch of external companies and organizations. And I will come more to the details of what it is and why it is relevant in that context a bit later on. But I extracted one of the work that a working group has been doing around responsible computing code. So understanding what is relevant from the developer or data scientist perspective. And why did I pick that one? I think looking at individuals within organizations, the most important factor is to make them aware about their role in the change that is happening. And having been a developer myself for some time in the early stages of my career, I know exactly that at that time when I was developing, I was taking any resource I could get. Obviously, at that time, there was limited resource or more limited resource than we have nowadays. But what I see is that nowadays, there is more to take and we will take more. So it's more compute, there's more storage, there's more possibility. So anyone will take everything that he or she will get. So that is not sustainable at the end. It's not sustainable in multiple perspectives. So one is that looking at the data side, for example, I'm collecting data, I'm using it perhaps for an experiment in an AI environment, and then what do I do with the data? Typically, I will just keep it somewhere on a disk. And if everyone is doing that, we are just accumulating what we call dark data. So dark data that has been used or has not been used, but is sitting somewhere. Most probably it's duplicated data because we are not working on live data. We have extracted it from somewhere, we have copied it somewhere, and it's just sitting there. It's occupying space on a disk. The disk is sitting somewhere in a data center. It's occupying space in the data center. And the data center needs to use energy to operate the environment, to cool it down. So a lot of activities that are tied to just my small AI experiment. The other part is when you look at UX design, modern UX design, it's not about a competition or beauty contest. It's really also being efficient in terms of what you use for creating UIs to make them sustainable. Then it's about reusability. It's about accessibility. It's about clarity in what you want and how you address people and the broadest population that you can imagine. And ultimately, also now thinking on the Gen AI side, how much of a training do you need? How much specific models do you need? And if you have set up an environment for training of models, how is that environment really utilized? So what do you do if you don't use it? Do you switch it off or you just keep it running? So a lot of awareness questions that are relevant for, let's say, growing population in AI for students at universities, but also for everyone working in commercial organizations already nowadays. You have heard me mentioning already responsive computing. So that might be a term that's not familiar to all of you. So here, a quick definition we came up now 3 years ago. And I think the most important aspect is that it is something that is addressing current and future challenges. It's around sustainability, ethics, and professionalism. And it's a holistic or systemic approach. So it's not looking at one specific area in itself, but it's looking more at the intersection of different capabilities. And that's why I think it's also good to link it back to the energy discussion that I have mentioned in the early beginning of my talk, as the energy or electricity companies are also working in energy systems. So they are dependent on the different levels of the network and the grid. Ultimately, responsible computing is advancing what we call here the quadruple bottom line. So it's about people, planet, prosperity, and participation. And I think although all four are very relevant, the last one is the most interesting part for us today. And linking back also to slides that I have had before, it's really about participation. So working with it and solving it, solving current problems, it's not about the others. In fact, it's about all of us. So we need to contribute. We need to make our mind, make up our mind and become active. So problems will not be solved because others will solve them. So and now what someone is doing today, if there is a need for a definition or explanation, we will typically go and ask an LLM to give something. So that's also what I've done. I did not only ask the question on what responsive computing is, that's an answer that you see on the left-hand side, but also to get some clarity on other terms that you may have heard already. And other terms in that similar context are green IT or sustainable computing. And my personal view, and also looking at the definitions that we got back here, is that responsible computing is more the overarching theme, whereby sustainable computing is specifically looking at the compute side only, and green IT is even a subset of sustainable computing. So if someone is talking about green IT, typically that person does not mean the overarching value of responsive computing. And just for comparison, I also took another large language model, and you see the definition on the lower left-hand side. So not for me to read that through. You can do that easily by yourself. But you see that the outcomes of asking LLMs is also sometimes different, and that also gives or tells us a lesson that you should not only rely on one gigantic model only, but you need to think about, are there more smaller models that are more appropriate and ultimately also more sustainable, because they did not require so much curated data, they did not require so much energy to get trained, and they will be most probably also more efficient for inference. And remember, for an LLM, over the lifetime of the LLM, more than 90% of the work with the LLM will be inference. So it's much more relevant to have a very efficient inference capability compared to the training capability. Let's have a quick look at the sustainable computing side nevertheless. So I think what we have seen is that there is an exponential growth in terms of data that will be generated. And the numbers here may be a bit outdated already, but it's the same direction. That, I think that's the important message here. It's still growing, growing, and growing. And I've had a quick discussion this morning also that in specific areas, we see even an increase in that data that will be helping us to overcome some of the shortages in terms of skills in the population over the next years. But we see also that there is then a need to work with that large amount of data. Then based on the new data and also new technologies, we see an increasing demand of electricity and energy. And we also see that something like the Dennard scaling or Dennard law is coming to an end. It's no longer correct, or it's no longer valid. And we see that if we just continue in the way that we have been doing in the last few years, there will be kind of shortage of energy. And a shortage of energy is something that cannot happen. So there is some things that need to be changed. And obviously, from the computing side, there are possibilities to work on it. And we see 3 stages here on that slide. On the left-hand side, it's kind of traditional changes. So mainly working on the efficiency of a data center. And data centers have a KPI. It's called PUE, Power Usage Efficiency Factor. That's how the efficiency of a data center is calculated. So it's between 1 and 2. 1 is absolutely perfect because all the energy that you put into the data center is used by the compute that is within the data center. I think that's only theoretically possible because you still have to do something that is housing, it's lighting, it's a bit of cooling at least. Good data centers that I'm aware of, for example, in Germany, are at 1.23 SPUE. So I think that's already very good, but it also depends on the environmental situation. So a data center in Italy might have different PUE than some data center in Norway, for example. That does not necessarily mean that the data center is more efficient in Norway, but there is less need for cooling and therefore less energy. Second area here is introducing accelerators, so new technology. So it's already addressing some of the chip design capabilities that are required or semiconductor capabilities. So what we see is that there is or that there will be most probably a rush for semiconductor capabilities in the future to come up with more to-the-point accelerators that will help to overcome some of the challenges that we see here also displayed on the chart. It's, for example, working with low precision in AI. So that's helping us to reduce the power consumption already. And then if we go onto the right-hand side, thinking about the new computational models, you can imagine that at that space, there you can find quantum computing technologies, you will find brain-inspired computing technologies. So all the things that sound very fascinating, some of them more real than others. And you obviously can also question why a quantum computer would be more efficient than a classical computer, and it's mainly due to the fact that the calculation is much more efficient. Of course, you will need, at least for the quantum computers that IBM is operating, some energy for the cooling, but the speed of calculation is just much better than for classical ones. There are other efforts that we are also doing and seeing on the open source side. So when we think about energy, when we think about sustainability, and also the compute side, it's important to be able to measure what's going on. And nowadays, often that has not been taken into consideration in the operating systems or in the environments that we have been built up in the past. So there is a project called Kepler. It's part of CNCF, and that helps to overcome some of these challenges and will provide more insight in guiding and operating an environment. As we wanted to have responsible computing become more broadly adopted, we said there is a need to have a manifesto for responsible computing. We said there are some values that are associated with it and some principles. The values are associated directly with what we call the responsible computing framework, something I will come up in the next slide. And the principles are more the cross-cutting aspects that are relevant when we think about the responsible computing environment. And some of them, I think, are very straightforward, like circularity or sustainability. There's some more relevant and more interesting, like authenticity or accountability. So it's really making sure who is accountability for what we are doing linked to responsible computing activities. And that's where we have now the responsible computing framework. So imagine that has been developed 3 years ago. I made a test a few months ago if this is still relevant nowadays. We're looking at Gen AI activities, and the outcome is that the model or the framework, as for any good framework, is not only relevant at the time when it's been created, but it's still relevant nowadays, even though the environment has changed and the context has changed. So I think, first of all, that was a good test for the framework itself. But let me quickly walk you through the different domains of the framework. And it has been on purpose built like this, so interacting and intersecting, because we see there is a cross-linkage between all the different components. And that was also for us a driver to move that forward. Because for individual areas, like the one that I mentioned for the data center, there were already the possibilities to measure impact and some focus on that area in the past, but not for the others and not for the intersection between the different ones. So on the right-hand side, 3 areas that are more on the technology aspects. On the left-hand side, 3 areas more on the societal side. And also that is showing that both aspects are relevant, equally relevant. So data center, I mentioned that one already. Responsible computing infrastructure is in fact what you put into a data center. So that's compute power, it's storage. This is where we see that circularity becomes more and more relevant. There is also a KPI that is calculated. It's called PCF, production carbon footprint. So that's not only looking at how much energy is used during the operation of a compute system in a data center, but it's taking the full life cycle of the system, including also the environmental impact of shipping it from the manufacturing site to the data center, environmental impact of creating the asset in the manufacturing site, and also the impact on recycling it. So a lot of discussions going on in that space also on the e-waste aspect. So what do we do with the electronics once they are end of life? So what are the possibilities and how can we recycle most part of it? we see that there has been a tremendous effort already done and some good achievements in bringing down the power consumption of the systems over the last years. But looking at the technologies that I mentioned in the slide before, I think there's still more to be done and more possibilities. I think in that space also material science is something that becomes relevant to make sure that we are finding new materials that is overcoming some of the challenges with rare earths that we will see in the future. Responsible computing code is then the awareness aspect mainly, but also how we document code. How do we make it accessible? And I think it's not only about coding, but it's also about the AI capabilities and more the AI capabilities and how we work with the AI in the future. On the left-hand side now, the three more societal-oriented aspects. It's about responsible computing data usage. And that's on one side touching on the data privacy activities. It's touching on the dark data aspects that I already mentioned in my talk. And it's really the foundation also for some of the process and for some of the works that we are doing through the framework. Responsible computing systems is then largely focused on ethical AI, but you can imagine that ethical AI is also having a close link to responsible computing data usage. It's having a link to the responsible compute aspects, and it needs to run somewhere. So all of this has some impact. And although we're talking about ethical AI, I think nowadays one of the terms that is broadly used is responsible AI. So it's going to that same direction. And responsible computing impact, ultimately, it's to make the right decisions to have a positive impact on society and onto people. So it's not only about the technology, it's not only about the best models, but it's also what we can achieve with it. Some examples here from our own work that we have been doing in that space alongside responsible computing. So it's talking about the accelerator, so that what you see on the left-hand side, it's going into low precision calculation for AI. The middle one is a very recent one. It's a brain-inspired chip that sees very good performance in specific areas today and very low energy consumption. So that might be the future, so the right-hand part on the sustainable computing slides that you have seen before. And then on the right-hand side, if you're interested in understanding more about the IBM and NASA collaboration on the geospatial foundation model. Now, I want to close that presentation mainly with an early idea, an early thought. I think when we look at energy, when we look at the AI in energy, when we look at the costs of AI and the cost of energy and that AI has a cost, I think it's relevant not just to talk about the cost, but it's really figuring out how can we calculate the values that we can get out of AI. And I thought we need to come up at some point in time with what I've called here an AI usage efficiency factor. I thought that factor is probably a function of an impact to the business, impact on environment, and impact on society. Now, that is kind of trying to solve the world. But the next steps that I would imagine is to start thinking about how to best frame this type of function. What are the information that we can already start with? What is the area that is more straightforward to address and to have solutions that are coming up? And why these three areas? Because typically AI will be applied in commercial organizations as well, or in government-related organizations, and there need to be an impact to those who are interacting with these organizations. And there also need to be an impact for the organization itself. So there need to be either a cost reduction, there need to be a new revenue, there need to be a service increase. But we should not only look at these more commercially oriented aspects, we should definitely also look at what we do with large language models or with foundation models or the application of this technology on the environment. So are we directly having an impact on the environment, or what is the negative impact because we are just using something that has a cost in terms of water, as I mentioned before, or a cost in electricity, as I also said before. And obviously, I think also we need to measure the societal impact of that technology. So if you have any ideas on how we would best continue in that ideation around the AI usage efficiency factor, happy to get in contact with you. If you would like to learn more about the responsible computing framework, then there is a recent HBR paper that has been published by a former colleague of mine and a professor from the University of Barcelona and myself. And there is a public site that is operated by the Object Management Group that is also running a responsible computing consortium. There you will find more publications, more discussions, and also an opportunity to contribute. That was the last slide of my talk. Thanks very much for the attention.
Thank you very much for your very intriguing talk. If there's any questions from the floor, please show your hand, then microphone will come to you. Any questions? Well, actually, while listening to your talk, it reminded me of some campaign on an SNS to expunge very old emails from your data, so that we can save energy altogether. And the day before yesterday, I believe some leaders of G7 announced AI code of conduct, but there was no direct mentioning on the energy consumption by these big AI models. So do you think it's necessary to announce some kind of ethical directions about energy saving by the AI community as a whole, and at the government level probably? Do you think that's possible? Or some big tech companies may volunteer to come up with some directions along that line as well. So I wonder whether you have any ideas on that.
Yeah, first of all, I think it's a very good question. So I think it's not necessarily about directions that needs to come from the government. I think it starts with the awareness. So if companies and governments are using this type of technologies, they need to be aware of the implications that the technology brings. And there is obviously also an energy or CO2 emission or water context that is often forgotten. So what I see in the discussions that I have with large organizations, some of them are rather advanced and they have put their own ESG targets out, and they are working with their supply chain to also make sure that the supply chain is adhering to the similar approach. Because you all know it's about scope 1, scope 2 for the internal aspect, and scope 3 for the supply chain. So if you want to achieve your targets, then you need to make sure that the supply chain in some form also works alongside it. Now in the current LM discussion or foundation model discussion, I think it's often really forgotten.
Another thing that I'd like to mention was data sharing. If a lot more data can be shared, then certainly that will lower the energy requirement. Can you suggest any possible solutions on that direction as well?
So I think what you mentioned is around open data concepts. I think it's an emerging topic, but it's not newly emerging. So it's emerging since some years already. I see some efforts happening. I think the work that's going on with Hugging Face, for example, to share some LLMs more in open space is part of it. But ultimately, there is some organization-specific data that will not make it into the open space. And the organization-specific data will then be a critical component to differentiate in the market.
Okay. If there is any questions from the audience, if not, we'll call this. Let's thank the speaker again for the very nice talk.
Thank you.
Please
Thank you very much.
Okay, our next speaker is Professor Sung-Hwan Lee from Korea University. And the title of his talk is NeuroTalk, Neural Representation Learning for Intention Decoding and Speech. Professor Lee is a distinguished university professor at Korea University, and he is also the director of Korea University Institute for AI. He actually founded the Korean AI Association, and he's also a fellow of IEEE and a member of Korean National Academy of Engineering. Okay, please welcome Professor Lee.
Thank you very much. So today I would like to introduce our recent pilot study for neural representation learning for intention decoding and speech synthesis. Brain-computer interface is a technology that interprets and delivers a user's intention to the external world without relying on any peripheral normal output pathways or peripheral nerves and muscles. So there are many interesting ongoing research projects around the world. Neuralink performs a human AI hybrid project. This aims for developing BCI communication to connect humans and the computers based on AI. They are trying to develop brain chip for measuring brain signals. Meta is carrying out a typing by brain project. They aim for typing 100 words per minute. Currently, as far as we know, about 8 words per minute is possible. Also, in MIT, alter ego project is going on. This is a speech synthesis technology using EMG signals. A typical brain signal measurement method is EEG. Signals are measured through electrodes attached on the scalp, while the electric signals are transmitted between the nerves of the active brain. So brain-to-speech technology is to convert brain signals into control commands or the voice of audible speech. It enables communication via brain signals instead of speaking out loud or entering text. There are some interesting applications of BTS technologies. Reading thought and instantly entering text rather than typing is possible. Human-computer interaction for smart control of external devices will be also possible, and patients with speech paralysis can engage in conversations via brain signals. There are many types of speeches. Speech can be categorized based on whether it includes voice output or physical movement of the articulators. Spoken speech is natural speech of speaking out loud. Silent speech is speech without voice output but with articulate movement. Imagined speech is mental speech without voice output or articulator movement. Imagined speech is therefore brain signals that occur when you imagine speaking without making a sound or moving the articulators. Language-associated brain areas over the temporal lobe is activated during the imagined speech. For example, Broca's area is for generating language, related to generating languages, and Wernicke's area is related to understanding languages. So this area, we made the best use of this area information. Let me briefly introduce our recent progress on this topic. We are focusing on translating the user's imagined speech into voice output. Using this system, intuitive BCI communication is possible just by silently imagining what the user wants to say. We aim for multi-class robust decoding to convey various commands. We investigate speech-related features. Understanding the speech-related features highly contributed to decoding user intention from brain activity. Also, neurophysiological mechanisms could be characterized by different band energy power features. For developing neural representation learning, we are designing a neural network that resembles the neural representations. So learning the neural representation from brain signals can contribute to improving the system's performance. For decoding semantic features of speech, we designed a semantic encoder that learns various sentences by considering the contextual meaning. And natural sentence could be probabilistically generated using the large language models. So let me show you the demonstration for our research by controlling the Google by our technology.
Hey, Google, how is the weather today?
It'll be sunny with a high of 87 and a low of 59. Right now it's 84 and sunny.
Hey, Google, turn the flashlight on.
Turning flashlight on.
Okay. So we also developed a diffusion model for improving imagined speech classification. This model learns meaningful features by removing randomly injected noise to classify user intentions. Therefore, we highly improved the classification performance of multi-class imagined speech. We also expanded the vocabulary set of imagined speech. Machine learning framework was developed to learn new words of unseen classes and newly added classes that have not been previously trained can be classified based on deep metric learning. Let me show you another demonstration.
Tom, help me.
I'm here. What can I do for you?
How's the weather today?
Look, it's sunny today. Do you need any more help?
Please turn on the TV.
Okay.
Okay, so we are also working on speech synthesis from brain signals. Speech synthesis framework using EEG and the voice to generate the user's own voice given the user's brain signals as an input. So in our case, domain transfer learning was applied to naturally map the imagined speech data and the target audio. For word-level voice synthesis using imagined speech, we successfully synthesized voice from word-level imagined speech brain signals using the high-frequency features. As a result, our model could reconstruct voice using the EEG of not only spoken speech, but also imagined speech. We are currently expanding this work into sentence-level natural speech synthesis. Okay, let me show you.
Hello.
This is original voice recording.
Hello.
This is synthesized data result from the brain signals for spoken speech. So let me show you the result for imagined speech.
Hello.
For sentence level voice synthesis using spoken speech, we trained phoneme information to generate natural sentences for more natural BCI communication. Spoken speech and silent speech have shown the potential to reconstruct natural voice from EEG signals. We are extending BTS to sentence level imagined speech, while speech synthesis using spoken speech brain signals have shown the potential. Imagined speech-based speech generation is still challenging. So imagined speech-based communication can be addressed by gradually expanding from phonemes to generate natural sentences. So let me show you the final demo.
여기에서 가까운 곳에 서점이 있나요? 가까운 시일 내에 한번 댁으로 찾아가겠습니다. 범인은 20대 중반에서 후반의 남성으로 보입니다.
So mimed speech and imagined speech.
모든 게 궁금해.
This is mimed speech. This is imagined speech. No articulation, movement.
여기에서 가까운 곳에 서점이 있나요?
Recorded audio.
거기서 누가 운영 곳에 서점이 있어요.
This is synthesized speech.
범인은 20대 중반에서 후반의 남성으로 보입니다.
This is recorded audio.
범위를 50개 분할해서 꿀판을 단서
This is
두고입니다.
synthesized speech. Result of our result. Okay, thank you for your attention.
Thank you, Professor Lee, for a very interesting talk with interesting demos. Is there any questions from the audience on the floor?
Very impressive to hear this and to hear the great progress.
Thank you.
So I'm wondering, do you need to train specifically to the individual, or can you transfer? This was not so clear for me.
So you are asking about the data training, you mean?
Yeah.
So we collected the data individually. So and annotated the contents for the data.
Mm-hmm. So have you, if you think about this, would assume that there would be enough data, right?
Mm-hmm.
Would you be able to also transfer between people?
Yes. We are working on transfer learning issues because the data is very limited. So we collected in our lab. We are collecting many different data. So we are going to make the best use of the pre-trained data for different applications. Thank you.
Any other questions? Professor Lee, I have a question. During your talk, you mentioned semantic features.
Mhm.
So I thought, will it be possible to generate a different sentence but with the same meaning? Because I don't know whether brain signal will be the same if I say, oh, I want to see the TV, or in the same meaning, I can say, oh, so please someone turn on the TV. Those two are actually having the same intention and same meaning, but with different surface structure. So I was wondering whether there is any differences in brain signals when I imagine two different sentences, but with the same meaning and same intention.
Very interesting question. So I think that we didn't make any experiment for comparing your issues.
Right.
But I think the representation will be different even though they have a very similar semantic meanings. So if the data is different,
Even at the word level, maybe? I mean, there are a lot of synonyms, and you can test whether brain signals are more or less the same between the
Well-
synonyms or very far apart.
so
I'm just
don't know.
curious.
So I don't know. Maybe my student can answer to that. Soyeon,
we can take it.
can you answer that?
Hello, my name is Soyeon Lee, and I'm a PhD student in Professor Sungwon Lee's lab. And the question that Professor Beck said is really important question in the field of BCI. So we are now expanding our work to the semantic level decoding. And currently in the demo videos that our professor showed before are basically based on language decoding based on the audio sound. So we're basically decoding the speech sound. But if we expand it to the semantic level, we can also decode the meaning that the user really wants to convey. So as Professor Beck said, if we decode semantic levels, then if the user imagines like, I want to drink water, then the output can be like, please give me a water. So we're now working on that. And if it's like successfully developed, we can also convey really various commands, or we can provide really intuitive communication. So we're now working on that.
Okay, thank you. Is there any other questions from the audience? If not, let's thank the speaker.
Thank you.
Okay. Okay, that closes our session, Cluster 3 AI for Scientific and Social Challenges. Let's thank all the speakers one more time with big hands. Okay, at 11:12, there'll be a keynote speech here at the Great Hall. So after a short break, please come back. Thank you.
Distinguished guests, ladies and gentlemen, good morning and welcome to the Korea AI Summit 2023. And please allow me to introduce myself. My name is Jiyoung Jessica Park, and I've given the honor of hosting today's conference. 여러분 안녕하십니까? 반갑습니다. First and foremost, I would like to express my sincere gratitude to our participants for joining us here today out of your busy schedules. The theme of this year's conference is AI-powered innovation, which is a very timely and relevant topic to pull the collective wisdom of AI experts at home and abroad, as we are ushering in the era of artificial intelligence. And today, we will be able to think about the present and future of AI, as well as its related challenges by delving into our topics. The Korea AI Summit 2023 is being broadcast on our YouTube channel named Korea AI Summit. And I'm very delighted to live stream today's conference, as we'll be able to reach a wider audience with fruitful and informative presentations and discussions. Now, without further ado, let us begin with our first keynote speech. And for that, please allow me to introduce Professor Irfan Issa, who'll be talking about generative AI and responsible AI. Ladies and gentlemen, please welcome him with a big round of applause.
Thank you. Everybody can hear me? All right. Let's go back one. So it's, of course, a distinct pleasure and honor for me to be here attending this conference, the summit. I wanted to thank the organizers for inviting me. I'm assuming this crowd has some amazing professors and some future AI stars and students. And of course, there's a whole lot of online people that will be also listening in. What I'd like to do today is, one, of course, enjoying my visit. Since yesterday, I visited some of the local companies and I met with many professors. A lot of great stuff going on in AI in Korea. And what I'd like to do today is give you a little bit of sense of my thinking of what's going on in this field and also showcase some of the work my team is doing in this space. So my research area is computer vision. What I've been interested in for a long time is how do we build machines that can see, and specifically the area that I work on is how do you actually understand content that's in a dynamic scene with videos? That's been a large part of the work that my team has been doing, both at Google and at Georgia Tech. And of course, within that context, we try to do work on improving the qualities of video, enhancing the content in a video, but also understanding what's in a video, what is happening in a video. And we also understand how do you use this to build better machines that can respond to those types of things. Then also really getting into the content of the whole context of how do you create content. And we'll show you examples of that kind of stuff. In addition to that, I'm also been very interested in understanding social media and how social media is leveraging the whole concept of video, how is it being shared, distributed, and stuff. Today, what I'm going to do is, of course, talk a little bit about one specific topic. But before I go on, I wanted to make sure to thank that this is work that I represent, but it's work done by a lot of people. This is a good chunk of people at Google that have worked on these types of things. Specifically, we'll be talking about work by Ki-hook, who's actually from Korea and was here last year to give a talk about generative AI and stuff like that. And then also Lou and Jose. This set of people here are actually from a team that's either overseen by me, myself, managed by myself, and also somebody many of you may know, Bill Freeman from MIT and also at Google. Just a list of publications for you to kind of, so these are publications from just the last 2 years that are in the topic of the kind of work that I'm going to talk about today. Before we get on to the topic at hand, I want to make sure that you understand this. Today, I'm going to be oversimplifying a whole lot of things. These are larger scale, multi-year projects with a lot of different types of things going on. So please bear with me. Also, this is some of its ongoing work, even though most of it's published. Also, since I'm representing a large chunk of people, the American term we use, a phone a friend, that if you really ask me a hard question, I might have to call a friend of mine in Boston or somewhere like that to be able to answer this question because, you know, there's a whole lot of work going on. Just to situate this, let's look at this whole timeline of AI. We're talking about AI and how it's going to change and impact a whole lot of things. I mean, AI has been around for a while. I mean, people talk about AI from the foundational years of 1940, where Turing talked about some of those concepts. The term AI was, coined in 1956. A lot has happened in this field. We have done amazing things about creating things like, for example, agents that can interact, recommendation systems, and all of that kind of stuff. Lots going on in understanding content and also how do you actually use this to create responsive systems to kind of answer some of the questions we're interested in. All of them aimed at making us more effective at what we want to do. But in the last 5-6 years, there has been some amazing progress. Some of it's, of course, been aimed at understanding context and content, that is, images, text, language, and everything else. But recently, there has been a whole lot of work on trying to also generate some of this. And that's where generative AI has kind of come in. And we have seen things like, just in the last 2 years, a whole lot of systems that can generate content because now we've done a really good job of analyzing all of this. Being able to read all of that's been written on the internet has allowed our machines to be able to at least use some of the categorization to be able to then reconstruct some of it. And we'll talk about some examples of that. And that's where I think some of this kind of excitement around AI has reached a new level. All of a sudden, many of us have been working in AI for 30 plus years. Now we mention AI, people think they know what we do. And actually, that's exciting in some ways. So just to help situate this, let's talk a little bit about generative models. which are the foundations of generative AI. Mostly, as I said, a large chunk of the work in the past was understanding it. Now we're talking about how to generate it based on what we have supposedly understood. There are many new techniques have come about, variational encoders that came in just in 2014, just about 10 years or so. Then we basically done GANs, and then more recently, we've actually done work on diffusion models and transformers. Most of my talk will be talking about transformers as a tool that we can use to help us do generative AI. But again, there are connections to all of these types of other technologies that exist. So just to help us understand this, transformers are basically initially came in because they wanted to model language translations. So this is some of the root works around kind of large language models is can you actually build these types of recurrent neural networks that can actually model language and also start kind of getting towards understanding large language models. They're well suited for information processing across the board, and really kind of at the core of it is really aimed at using LLMs or modeling LLMs. Diffusion, which is much more aimed at also kind of modeling different scales of information. So, for example, looking at how would something like, in this case, salt diffuse into a liquid? How would you actually take small amounts of signals and grow it and differentiate and diffuse it over large models? Again, this is used widely to generate new content, the kinds of stuff we have seen. Type in text, it generates an image of different types of things. Both these methods have the advantage that you can really kind of pair them with an LLM to generate images from text and also videos. So how do you take a large-scale model of language that has categorized associations with what's the word and what an image of that might look like can be used to now generate newer prompts, and those newer prompts can be used to generate newer visual output. And we'll see examples of that. I always kind of remind ourselves that in computer vision, many of us have been always interested in this paradigm. Give me a picture, and I want it to generate a text for that picture. That is a description of what that picture is, a label for that picture. This new paradigm has gone towards the opposite direction. That is, give me text, and I want to generate image, or I want to generate some sort of a video or media to support it. So now let's dive into a few specific examples. I'm going to talk initially about the whole concept of how we can generate images by using text or any other type of similar input. So this is one work we just did a while ago at CVPR 2022, which was about how to use the transformers to generate images. Now, one of the things with transformers, as I said, remember, it was used for doing text processing. So it was always sequential, that you would actually parse everything and look for tokens in something, in case of language, language tokens, and use that in a sequential manner to understand what is the content. And then after that, you would encode it. So one of the things in this paper was done was, how do you, for example, look at that but not be constrained by how you do scan rate of images? Remember, if it's an image, you have to start at scan ratios, go line by line to extract tokens. This is computationally expensive and also requires a lot of data. So one of the things we did in this case was look for masked tokens. So basically that allowed us to now look at an image and look for specific signals over an image by not just looking at a scan rate, but kind of randomly looking for a footprint over an image and using that to encode the information. And using those types of things and using bidirectional transformers, we were able to then actually encode images much more effectively and efficiently. So that was the kind of work that happened with Maskit. Again, a transformer that was kind of much better at encoding images than others. This led to this work called Muse, and I'll talk a little bit about that too, which was, again, an attempt at trying to do this, but now bring into this encoder an ability to do text-based image generation. The advance of Muse, the advances were basically is that it used a discrete diffusion paradigm. Now, once you start thinking about it, remember a diffusion in an image would be pixels would generate over the space-time of the width and height of an image. Well, when you do a mask and you look for a fingerprint on that one, now you can generate an image pretty much in the same manner as diffusion, where now you're no longer just doing scan rate, but you're kind of sampling over the space and time of an image. It's faster. It also actually has a lot more fidelity of the data that we're looking at, and also can leverage things like CLIP and others that you may have heard about that use this to understand what the image is. Also allows for flexibility, and I'll show the example of that in a second. So basically, the idea was predict all of the masked image tokens on the whole XY, the width and height of an image by looking at specific tokens, look for different ways of encoding it, and use that to generate a set of masked tokens, which then could be gone through a transformer to generate a predicted set of tokens. Just to kind of situate this again, let's talk about how we can now do text plus image to generate an image. So of course, let's just take the word of text to image. We've given a text, we have modeled it, created a model, text encoder goes into the text embedding, and then go to the base transformer, and then it can reconstruct tokens based on what it's learned. But we want to make this a little bit more, let's say, general. So we add another whole layer, which now says is, okay, it's not just text and image, but give it a text plus image to generate another image. So you want to condition with an existing image. That allows you to hold the whole paradigm of image editing, because now you're taking an image and a text and combining those within the architecture to be able to generate a new image, and that basically allows you to create newer content. So let's take this. This is the basic premise of Muse, and using this kind of stuff, now we can basically say things like, generate me an image, 3 flowers, fuzzy, dusk, soft orange, a watercolor painting, foggy lights, soft noise. And you see these beautiful types of images being generated, especially since it's trained on a whole lot of natural and non-natural images available on the internet. This is a powerful technique and can be used to generate, of course, all kinds of synthetic images. You can see city lines for New York City. You can change things like, or you can change the misty sky and stuff. Again, assuming is the world's data has images of a city, perhaps even New York City, under different weather conditions, and now we can model all those. So this is something, again, I do note that, of course, I work at Georgia Tech, but I'm also at Google. And one of the dreams that comes true from my kind of work is that we can actually write some of the best research papers, and we can actually then deploy them into real systems that can be used by people. So here is an example of some of the stuff that I talked about with generative AI that has now been deployed and running on a Pixel 8 that was just announced about 3 weeks ago. I know you don't have Pixel 8s here, but if anybody wants to see it, I have one in my hand. And this allows us to now kind of start doing what I just talked about, editing in a system in real time on a mobile phone. Let's see what that means. So here is one thing which was existed for a while. It had been announced, I think, at Pixel 6, was something called the Magic Eraser. That would let you erase unwanted parts of an image and do in-painting and backfill. It worked very well. It wasn't using any generative media, but using some of the new generative AI stuff and using MaskKit that I talked about, we can now do a much better job of filling in mixed pixels. So here we take care, get rid of one of those people that we don't want in this instance, and it generated the chair quite well. Of course, those of us who are hardcore at this will find that this is not perfect, and there will be examples where we'll see that, yeah, there are some artifacts. But the goal of this generative AI-based work is that it's actually getting better. And of course, just to point this out, this is an algorithm based on MaskKit that's running on device on a Pixel 8 Pro. So this is one of the first few instances of really deploying this kind of stuff in the wild. Many examples of this. I was in Paris for ICCV. The previous version, when you did remove different types of things, left some artifacts. It gets better. Similarly, again, different types of things. And you can see some examples of things that basically have issues, like this part here is much better. So there are many examples of these kinds of things that can happen. Another set of examples, we can remove things. It does kind of create something that may not be real, but it does a very good job of doing in-painting using these methods. Another thing we added in this one was we wanted to kind of make sure that when Magic Eraser was happening, sometimes a perfect example would be is a person is holding a bike, we would get rid of the person and the bike would be there on its own. Well, we want to find connected objects and also remove them and do backfill on those types of things. This was in addition types of things. Again, when you have a person on a bicycle, it's important to remove the person and the bicycle, not just the person. So these types of things, can you detect them? And then we can do hole fillings to actually do a much better job. Again, something which is now running on both Google Photos and also on Pixel 8. Here's another example. This is actually a magic editor that does a lot more than just remove and backfill types of things. This is a picture from an event I was at. And if you notice that, we took a picture of me and my wife, but there are other people in the background. I know both those people. They're really good friends of mine, but I wanted a picture without them in the background, and you can generate this kind of stuff. Just to note, this algorithm does not work on device. This does send things up to the cloud to do a better job of these types of things. Just another example. All of a sudden you can see a whole lot of people have been removed. The picture, if you look hard at it, you might see some things are wrong. So it's not perfect, but it is something that works quite well. So just one example how we can do this on the world of images. Now let's actually talk about style. That is that not only do I want to generate an image, but I want to also generate an image with a specific style. Now, every time we look at it, we basically always seen all of this work with even DALL-E and say, somebody says, paint me an image of a flower in the style of Da Vinci or DALL-E or somebody else. That was kind of something we did. But we wanted to do something different. We wanted to say, generate an image of X looking like this picture. And one example only. And I'll show you examples of that. So here was one of our test cases. Given an Android picture, in this case, I show 5 examples. Can we generate, now I say, is make a bird look like that one example. Of course, all of the other work that was done with Muse is done before, so the model has been trained and is ready. Now we're actually adding kind of more one-shot or K-shot transfer on these types of things. And using this, now we can generate newer set of logos based on just this one, in this case 5, but it can be also one example. This is a NeurIPS paper. You can read about it more in detail. The key idea in this one was basically can we disentangle style with content. The content was bird, but bird in that style of the Android example. So we basically wanted to kind of do this stuff. And it basically what it does, it extracts a separate level of information for style. There's a classic paper by Bill Freeman and Tannenbaum, J.P. Tannenbaum on separating style and content. And this kind of now it takes all of the new technology to solve this problem. So again, the same architecture that we saw before, that basically text is there, but we also start off with an image and use that image, except that now we want to change the image to a style image. And then using the style image, we can change the base transformer. By the way, I didn't get into it. There's a base transformer and then also something to improve the resolution of the images and stuff like that, because we want to actually scale the image up to more pixels. That also uses a whole lot of this kind of stuff, not details in the paper. But now we basically, in the base transformer, add another attention layer, and this is much more driven by the style. So that's how we separate out the style and the content. And of course, this requires more training of different types of things, more parameter tuning, all of that kind of stuff. But it's something, again, with 1,000 steps, optimization steps, we can generate this. I'm not going to get into details, but this allows us to infuse style back in to the base transformer in a different form. And now, all of the equations, I had to put one in just to showcase that we do have equations in there, but allows us to basically now put in a separate term for controls and also taking the input from a text. So here are now sets of examples. So here a style reference is a pictorial of a pizza. Using that one example, now somebody can type in toothpaste in the style of their style reference, and we can start generating a whole lot of class of different types of things out of it. You can start, it gets really a lot of fun. You can play around with this extensively. Again, in this case, some simple pictorials. You can generate a lot of things. This is the kind of stuff, by the way, people in the design and art field have gotten really excited about, because it allows them to now kind of start generating next scale types of output. It's not about replacing those artists. It's more about giving them tools so they can be more effective. So many examples of this that we've played around with. And you can see these types of things here. This is the most interesting one. So the example image, the colorful flowers in the style, is the style reference image. This was Ki-hook's nephew who painted this. So Ki-hook asked his nephew, can you make this small diagram? One image, one example, we can generate a whole lot of examples out of this. So just by taking that one thing and the entire Muse system, basically, and all of this new self-attention and adaptation that we build in, you can type in a baby penguin, and notice it picks up different types of things. Now, can you explain all of it? I'm not sure. For example, why did it choose to make the penguin's body be green and the head be purple? I mean, there is purple and green in the original figure, but we don't know what the context is and how those pixels were chosen or those colors were chosen. But it allows for quite a bit of really kind of interesting design outputs. We can actually use this to start generating complete fonts from single images. So you can basically do typography out of this kind of stuff and all kinds of additional designs. Just to show you examples, and again, there's the entire website has all of the details on it. Just again, the same example. This is research we did, wrote a paper, but at Google, we were able to then deploy both Muse and StyleDrop on the Google Cloud platform. It's on limited release right now to the premium customers of Google Cloud, so they can also play around with this kind of a tool and generate their own kinds of images and stuff like that. I'm not going to show the video. There's a whole video of how they expect people to be using these kinds of stuff. All right, so one thing I'm always talking about it is we've taken a whole lot of work in my career that's been around on images, and I always ask the question is, how can we take this to the world of video? So by now, you shouldn't be surprised. What we did was we looked at all of this kind of work on images, and now we're asking the question, can we use this to generate videos? So this is an example of what we're going to kind of talk about. This is also a large-scale collaboration between my team at Georgia Tech, Google, and people at Carnegie Mellon. And this is also something is online and available. This was a CVPR paper. We have extended that since. This video you see, by the way, and I'll show you examples of it, has been extended to be much broader. So the only footage we had in this case was a cell phone of just the balloon. The rest of it is all generated. So the idea here is create a model like Muse, except for video, that is also capable of doing a lot of different tasks. So the same tool can allow you to do frame prediction, frame interpolation, so you're just giving two images, finding out all potential images in between by doing generative media and generating video out of it. You can do outpainting, crop out different things, can generate the rest of the image or the video. In painting, there's something missing. We want to fill that hole. And also crazy things like I have a class condition from some database that shows how an action of squeeze something looks like. And then we give it a first frame of a hand in front of something. And it basically, since it now knows the squeeze action, can generate a video of you squeezing this, in this case, I think just like a plastic case. Kind of crazy. It's not perfect. I don't claim it is perfect, but it's something crazy that is just from first image and basically a sentence saying what to do with it. So just like in the previous work, I'm going to explain a little bit of it. It's the same architecture that we have for Magwit. Of course, there's a lot more details on trying to do this, but the biggest idea was now we're talking about these tokens that are actually 3D tokens. So they look at a segment that is in space and time. So initially in the case of images, we were looking at these mask tokens, which were basically small regions in an image, but now we take that and actually do this on a n frame sequence. Mostly the n is about 8 frames, 8 frame sequences, and build these 3D tokens. So the same architecture applied to a lot more data. And that allows us to kind of allowing basically the same kind of a way. It's compact representation. Of course, it's video, so it's a lot more bigger than just images. And using that, we can basically start playing around with things like, for example, we can reconstruct exactly from those tokens. So here is just an example of a 600 times compression, because we basically use the tokenizer to tokenize the image and use the tokens to regenerate the same videos per frame. Almost indistinguishable. Some news work that's going on in this one is basically showing that we're actually at the state of the art of really doing compression and these types of things too. Again, not going into details, but the same architecture as before, except that now we can use the same model with the tokenizer, except that now we take some parts out, let's say, doing outpainting, where we get rid of some of the regions. It can fill that in because it's seen those types of things in other data sets and other types of things, and it knows the context of how to fill those holes in. We can use it for in-painting, out-painting. And this is the example that I wanted to kind of say is looking at this as the architecture. So while it's not diffusion, it has a little bit of a flavor of diffusion that is basically it's distributing the image and generating this randomly by pixelating it and using those pixels at a random masking to generate this. And again, lots of things can be generated out of this. Frame interpolation, again, you see 2 frames of cup being filled. It can generate a whole lot of it. Again, I wouldn't say perfect, but considering it's coming in from very little data, it's pretty impressive. And again, I can show you gazillions of examples. I'm going to go through this fast. And all of these videos, by the way, are available online. But again, also in some of the instances, taking one image of me holding something, not me in this instance, somebody, and saying, okay, class conditional of generating a video of somebody moving this object down. And it can generate those types of things. So other types of things can be generated out of it. I'll show you some problems with this in a bit, and of course, because of the way the model is built, it's much more efficient. It's still video, so it takes a lot of compute time, but it's one of the fastest systems out there. Going into details on this one. This was what I was talking about. So, you take a cell phone image, you want to generate the entire panorama out of it. It can generate those kinds of things, and it actually also figures out, some of the other work we'd done almost 20 years ago was video textures, and this is kind of now doing video textures and graph cut textures with the whole generative media. Another example, you just saw the small split, and this one is a pan and zoom. It can generate those types of things. The resolution is still, somewhere below 512 on these types of things, but it's something we're working on improving. Shown examples of frame prediction. Here it actually also figures out that the water could be flowing where it was never there before. And it can animate things, generate a whole lot of things and stuff like that. We can start doing simple camera moves and stuff like that. Again, many examples of all, and this is one model that does it all. Hopefully I'll get to some examples of this, but you see many examples of this. So here again, this action stuff that is now we can generate from different types of things and a textual description, a little bit of an action based on it has seen other people do something or other images that do something similar. Can be used for driving. These are all actually classical data sets. The reason I wanted to show you this is it doesn't know about camera angles. So it doesn't know about 3D. So of course, when you change the viewpoint, it does see a lot of warping. So that's what you can see with the book and the cup right now. So it doesn't have the 3D correct because it doesn't know about these things. And the chair also looks a little warped in between. Again, I'm going to skip over this. Skip over this too. More examples, more examples. So next part of it is actually, we already have a next version of this one. And I kind of gave you examples of this one, is we've actually improved the tokenizer to even be better than it was in the CVPR paper. So another paper is in review right now. And this allows us to even do better compression, better modeling, and the size of the model is almost 1 order of the magnitude smaller than the previous one. More on that one we'll show you, but some of the examples, of course, we have now added text to image, to text to video and this kind of stuff. So we can generate things like, these types of short videos. Panda, mad scientists mixing sparkling chemicals at ArtStation types of things. Again, these types of things. Yes, you can notice some of the warping is not correct, but it's quite impressive that we can generate these types of things and stuff like that. And again, some of the stuff is state-of-the-art results and more examples of this kind of stuff. Yes, people who know about panda or teddy bears and trains see some more artifacts than most of us do, but still a lot of interesting things can be seen out of this generation. All right, I'm gonna now end with just a kind of a talk about it. I was gonna talk a lot more about it, but if you want, there was a great talk about responsible AI just before mine, and I think you should listen to that one more carefully. But I just wanted to, especially since we're talking about generative AI and generating a lot of content, we have to be a little bit more thoughtful as to what we're going to do with this stuff. So, the whole concept of AI is, challenging in many different ways. Sorry, the slide is not working as well as it should be. But, There's issues around plagiarism and copyright with generative AI, right? There are issues around misinformation, disinformation. People can generate valuable information because it's an arms race, right? These are new tools. People can use this to generate content that is going to bring them value, but could be something perhaps not appropriate or ethical or moral. It's going to impact jobs. The tagline that everybody comes and tells us is, oh, by the way, when you start having these tools of generative AI, it's going to replace artists who are going to generate these types of things. True, but at the same time, here is my basic way of thinking about it, is that it's not just, we shouldn't just be worrying about, at least now, so the way I put it is, ask not when AI will replace people. Ask when people using AI will replace people not using AI. Because AI is going to become a tool for doing these types of things more and more. Lots of other types of things going on, but there's a lot of scare, for fear about what it can do for us. But I think we need to also be very careful on how we develop it. There is issue around what data to use, how to be fair about this data. And those questions have been there from a long time ago. I remind everybody in the world of photography, you may have seen some things called the Claire charts, which were very specifically designed for people with much clearer white skin, which doesn't really work on calibrating cameras for others. And this was in the 60s, before digital photography existed. So collecting data appropriately is an important part of how we do things. This is an example of work that me and my team did many years ago. So there's work that we did on kind of just using images to generate more images. And this was the pre-generative AI domain, so 2000, 2005 era. And we basically were using techniques along the lines of texture synthesis to take some examples of something and copying them over, but copying them with a little bit of a different stochastic signal to vary it in different ways so it would look different. So here is an example, and this was a paper we wrote called content-based image synthesis. Everybody was doing content-based image retrieval. We had a very small idea. By the way, many other people have done much more impressive work in this area since then than we have, but this was something we earlier just did. And basically the idea was just take one image, but look at the clouds from another image. And by just doing a little bit of stochastic signal matching and texture synthesis, we can change the background of this image to be dark clouds. Now, this is a perfect example of basically now manipulating an image to change the story, right? Initially, it was somebody in front of clear, sunny skies. Now, just by small manipulation, we can make it be dark skies. This is a very innocuous example, but you can imagine just simple edits like this can be used for doing a lot of damage to the world. There have been instances, of course, you've heard about this in the political arenas, of people manipulating images, and they're doing things that they actually never did, and doing this for, of course, celebrities and stuff, and also for normal people. So these are something we have to be very thoughtful of. And yes, we are developing these tools to provide you editing capabilities of removing people on your cell phones. That even could be misused. So we have to be very careful of these types of things. I always kind of say is that technology has been taking over jobs for a long time, and that continues. It's also our charter. Some of us are in the field of education, is to have to educate people to kind of use the technology and develop new technology at the same time, because it's just been the evolution of society. Jobs are always up for change. But we have to kind of always, especially as some of us are educators and also working in the discipline, change those things around appropriately. I always like to also show this example that we've been writing emails for a while, and all of a sudden we noticed that email sentences were being completed. That was also an example of some of the earlier, not as large language models, but the precursor to what we see. It was actually finishing sentences because it figured out and learned the model of how sentences are written, and that was doing it. And now we're in an era where that's basically gotten us to writing things that are somewhat interesting, but at the same time could have artifacts. And finally, I always try to remind myself, we're in the era of machine learning. That is that, basically, and there are many students in this room, we all know that every magic parameters are being used to edit things around, and we play around with those types of things a lot. With that, I'm just going to say thank you for listening. Any questions?
Thank you very much for your insights. So I think generative AI is one of the most hottest issues that is trending these days. All right, so we are now open for questions. If you have any questions, please raise your hand. We will deliver the microphone.
Yes, Sean. Don't ask a hard question.
You have presented very impressive results, and it's very cool, but as you said, it's not always perfect. And for many of these applications, and if you want them to run on phones, it has to be perfect, because otherwise people won't use them. Or maybe they will, I don't know. What do you think?
So I agree definitely. If the goal is to have an automatic output, it can be perfect. But if it's an editing process, it could be part of the process. That is, I'm trying to accomplish something. And using that process, I'm actually looking and iterating over it. And in that case, the iteration process helps you do this kind of stuff. But at the same time, overall, you're right. If it gets to be perfect, what's the real output of this kind of stuff? In case of images on your cell phones and stuff like that, if the task is to improve the lighting of a photograph and high dynamic range and all that kind of stuff, those are actually now showing an improved image. But in my case, I mean, I teach computational photography a whole lot, and one of the things I say is some of the HDR images we see on the internet nowadays are actually even what our human vision system doesn't see. It's showing the dynamic range of clouds to the moon in the same image. I mean, that's not a real image. And even our vision system does not see that kind of stuff. So people are extending what reality is in these types of things. And now when we get into things like being able to show style, that goes even further on trying to extend this. So bottom line is, these are tools. Now we have to be the responsible users of those tools as to how we can play around with them to answer some of the hard questions. Yes, Ivan.
Thank you for very inspiring and impressive results. Wonder specifically for video, right? So it seems that mistakes which are happening, it's quite a bit about geometry and about physical properties. Like I think was a pen example, which I imagine if you pull it a bit more, I mean, predicting that it will fall down or generating video that will fall down, probably still quite hard. I wonder, what are your thoughts, like going over this barrier?
On the viewpoint changes. Oh, sorry. We are working on the viewpoint changes because that actually is challenged a little bit by the data, right? If we had data that could actually show the viewpoint changes, we can start modeling that kind of stuff. This is where a lot of sim work becomes very important. And as you know, in the 3D world, there's a whole domain of nerves that actually allows you to get this kind of data. So on the 3D side, I think there is hope. On the action side, it's a little trickier. Now, I think we can do a good job on the data that's available for things like, let's say cooking or assembling things and stuff like that, because there's a significant amount of data for those types of things. But it won't be available for all general things. But some of the other things that are interesting is, how can this be used for, let's say, autonomous driving, at least to generate more contextually aware data that could be used to play around with it. So there are potential applications that could come in. But yes, I completely agree. This is hard. And that's one of the reasons I'm excited about it.
Thank you very much. Unfortunately, we will have to wrap up there in consideration of the time. So that leads us to the end of the first keynote speech. Thank you very much, Professor, once again. Please give him a big hand once again. Thank you.